Hey everyone! Today we're going to be talking about inverse responses and time delays. So to first talk about inverse responses, this takes us back to the previous lecture on our higher order dynamics, where we identified zeros and poles. Now we talked about with those what happens if we're in a right-hand side plane or the left-hand side plane. Where the left-hand side we're able to actually converge, and the right-hand side things end up becoming very highly dynamic and kind of go on forever. So on this sense, we are talking today with inverse response about the zeros specifically, which is the numerator-based terms. Now, the zeros don't directly impact its stability, but they can influence the overall dynamic behavior of a system. So say that we were in a system that had a steady state value, and at time equals 0, we try to reach a new steady state. So here we're modeling our control variable or our output. So I'll go ahead and just say control variable over time. And so as we're moving along, notice there's a strange drop where first we're going down before we actually end up going up towards our steady state value. This is happening as the system has to make a switch or a change, and our 0 is real and greater than 0. Zeros greater than zeros, yes, but 0 being the operative term for what's happening in the numerator base expression compared to a pole. And so if we're in the right-hand plane for the 0, that means that we have to overcome that kind of influence, the dynamic behavior. You can think of this in a lot of different examples. If you change your steady state operation, yet your numerator based on transfer functions does have that 0 to be positive, then unfortunately you do have to consider there's going to be a quick change that will eventually lead you back into your normalized stability. So this actually does happen pretty commonly, even in distillation columns. So let's consider a real example for this, or mostly real. We're going to build a transfer function that's going to allow us to go in, and we're going to have an x of s term that splits off into two pieces, and then it's going to recombine. We're going to do positive, positive to recombine and yield out y of s. And now in our transfers here, we have two different transfer functions. We have number 1 and number 2. The first one is going to be 5 over 10s plus 1. The second one is going to be negative 1 over s plus 1. So say that we wanted to build out our total transfer function then. That's going to be equivalent to g of s, which is y over s over x of s. And that is going to be the summation of both of these pieces. So we're going to have the sum of g1 of s and g2 of s. Now, that's because we're splitting off into a parallel system. If they were in series, we would multiply. And so g of s is now the direct sum of 5 over 10s plus 1 plus minus 1 over s plus 1. We need to combine these to get a singularized term, and we want to try and extract out our zeros and our poles. So let's multiply the first piece here by s plus 1 over s plus 1. And we'll multiply the second piece by 10s plus 1 over 10s plus 1. That'll leave us with a common denominator, and both of those are just multiplied by 1. So that's now 5 times s plus 1 over 10s plus 1 times s plus 1 minus 1 times 10s plus 1. We can combine like terms on top, and ultimately we have 5s plus 5 minus 10s plus 1, so that's minus 5s, and that's plus 5 minus 1 is going to be plus 4 over 10s plus 1, s plus 1. Now, when we think about these terms together and we're trying to group things out, our numerator term is what's going to give us our zeros, and the denominator gives us our poles. And so with each of these specific terms, remember, the 0 specifically is going to be based on the term itself divided by the time term. And that's going to be used for each of these. So if the 0 on top is going to be this singularized term, so that's 4 over our time term minus 5, but it's always minus of that, then that's going to be equal to directly 4 over 5. And our pole is going to be minus 1 over 10 for the first one, because that's the time term and that's the standard term. We want to keep it in the standard of 1 anyways. And then pole 2 would be the second one, so minus 1 over 1, which is just minus 1. And so what we see here is we have a positive 0 here, 4 over 5, And we have two poles directly. We have -1/10 and we have -1. So that's going to give us a lot of information about our system and how to recapitulate it, but we do know that we do in fact have an inverse response here. So we're going to be pretty stable, and that's because of these negative terms, and remember that. Those are the ones that tell us stability. But the top term means we're actually going to be modeling something out like this, where as we have a dynamic change in x of s, what's going to end up happening to y of s? So if x of s is like a step function, like it would be here, where this would model as delta x, then as we actually now have an influence of that change, the system will have to actually regulate a competition to then go back. And this dynamic behavior would be modeled like that. And so this is a standard example of how we think about a parallel arrangement and the influencing factors of different transfer functions on the overall system. And so while we're not influencing the stability necessarily, we are thinking about overall dynamic behaviors as we go back over, which does come back to our original discussion about what happens at each of these different conditions where we have an imaginary term and a real term. And so on that, we're next going to be talking a little bit about time delays. So I'll go ahead and erase the board and we will start that discussion. Time delays are natural phenomena that exist in essentially all systems. So say that we have fluid flowing through a pipe, and we're just going to assume it's turbulent for now. So it's going to be like straight lines of fluid just flowing through at any point in time. And that we're not going to have that like parabolic shape with, standard flow like laminar flow. And so in turbulent, we are assuming that across from point 1 to 2, this fluid on this side ends up on that side more or less instantaneously. But as it continues to flow through a velocity v, we are going to assume that as it spans the length L, we have some time involved that is lost. So that would be essentially the length of the pipe over the fluid velocity, which is length per time. Thus, we receive a time term back when we consider this. And that's going to be considered the time delay that it takes to go from 1 to 2. But that's natural. So say that we have a standard amount of flow and that we then increase the flow. And the change in that flow rate has to be met by point 2. But it's only started at point 1. Therefore, there is a time delay physically as it goes from 1 to 2 to make that kind of change and then change out the system's flow as it reaches 2, which maybe is the actual system itself and we're just flowing fluid in and the system is like a mixing tank. But we're just seeing that there is a delay as it goes from these points, and that's relevant to the time delay. So let's say that anything between, negative infinity to just before 0, my output function is at 0. So we're modeling it at 0. And maybe my input function is also at 0. So if that's true, then maybe they're both here at 0. But after time equals 0, we have a step function, and we're going to include a time delay to that step function. So maybe the step function starts immediately, but the output change of how it affects 2, or my y of t now, is going to be delayed. So we have to assume that based on whatever potential time delay that could exist to that system, we have to incorporate that in our step function, which then leads to that output effect. Notice the theta is in both spots because it's a continuous based time delay. And so on that mindset, we need to start factoring in time delays that may exist. So if my y of t now could be functioned as essentially y of t equals x of t minus theta, but with the step function in mind being t minus theta as well, then how would I perform the Laplace transform of this? Well, Laplace of y of t is equal to now the Laplace of x of t minus theta and my gamma t minus theta for my step function. That's going to be, for the first term, x of s. So now y of s will be x of s. But the second term is e to the negative s theta from our tables, and that we've solved before. So this would describe the relationship here, where then if we divide y of s by x of s, we would get g of s to be just e to the s theta. And now, unfortunately, we can't actually use a polynomial to factor a time delay. That's not going to work. But we can take an approximation for a polynomial. And so we talked about the Taylor series expansion to do that. Well, we can do the same type of expansion, but a Maclaurin series. So the Maclaurin series is done at t or x equals 0. So essentially, it's just a function at 0. So if f of x is based on f of 0 for my Taylor series, then how can we describe that function? Well, before, we would have said we want to describe e now to the x, which is f of x, and we want to do so using now f of 0, which is going to be standard for e to the x is f of 0 plus f prime, or derivative of 0, times x over 1 factorial plus the second derivative, x squared over 2 factorial, and so on. And so in this way, we would be able to say, okay, well, we know for a fact that the derivative of e to the x is e to the x. And we know the second derivative of that is also e to the x. And so all derivatives based on any n that could exist for those derivatives is f to the n for e of x, and that's always going to be equal to e of x. And so if I do that but I plug in 0, then that means these are always going to be equal to f of n e to the 0 is e to the 0 will always be 1. So all these terms will always be 1. And e to the x then becomes 1 plus x over 1 factorial plus x squared over 2 factorial, and so on. And we can now substitute whatever x may be. So say that in this case, x is equal to negative s theta. Then e to the s negative s theta is 1 plus x, which is now minus s theta over 1, plus negative s theta squared is going to be plus s squared theta squared over 4, and so on. But the good thing is, in almost all cases, we can take a truncated form of just this piece. Further, say that I had instead x equals s theta, just for fun. Then in that case, e to the s theta is going to be 1 plus s theta plus s squared theta squared over 4, and so on, where we would have an oscillating plus and minus in one system versus the other. And so say perhaps that you wanted to add these terms together, or you wanted to take the terms and work with them, like where maybe 1 is equal to e to the s theta times e to the minus s theta, which is the same as e to the s theta over s theta. Then that would be multiplying this whole term by that whole term, and so on and so forth. And these are different ways that people can start to approximate these. We can also think of it as these can be built off of halves. So e to the negative s theta over 2 times e to the s theta over 2. And if those terms are now going to be multiplied together, then what we're really starting to look at is how would this work for that multiplication? Or better, how can we consider e to the negative s theta over 2 over e to the s theta over 2? Because if we add that back up here, then that's just going to end up being, if these were both originally negative, that is e to the negative s theta based on additive property. So if e to the negative s theta could be based on its halves, and that gets rewritten like this, but we know that we can always solve for where there's r based on those halves, and it's always based on the first term, then on the numerator, we would have 1 minus s theta over 2, and the denominator would be 1 plus s theta over 2. And this then becomes its own approximation for how we would think of e to the negative s theta at any point. And notice that we're starting to get into an idea of, you're noticing this like s theta, 1 plus s theta, 1 minus s theta. That is our way of thinking about the poles, where in that case, say that we had 1 plus s theta. I mean, that looks very similar to 1 plus s times tau, or, you know, tau s plus 1 is essentially then theta s plus 1, where these are both time-based terms. But we're thinking of it as this is our standard time-based term for our system, and we have now a time delay term. So we're taking an approximation, essentially, that allows us to describe those time terms as thetas. And now, why would that be impactful? Why would that be helpful? Well, when we build out a system, it's easier and faster to model things in first order. And say that you had a system of g of s that was 10 times s minus 1 over this term of maybe 3s plus 1, 5s plus 1, 10s plus 1. That's not going to be first order anymore. That's going to be a lot of different orders. And we have a lot of things to consider based on poles and zeros that we might want to approximate for. So what would be faster is trying to turn this system into something that we can rapidly expand and make appear to be a first order system. But in doing so, we would want to consider some of these terms to actually act as time delays and approximate them as a time delay that would switch them into the numerator. And now this would be a really handy approach because they're not truly in the numerator themselves. They are e to the negative s theta, which means they're actually still in the denominator as e to the s theta or theta s. That works. We can do that. We can take some of these based on that. The only rule we really need to consider, or the main rule, if you will, is it's all based on what is the maximum time, we'll call penalty. What is the time penalty here? And it's going to be the greatest time-based term in the denominator, and that has to stay stationary. And then the other terms can be moved into the numerator as the e to the negative theta s, which is really just reapproximating. Because remember, if this is true, and that is essentially this, where this is all true, then I could say theoretically that 3s plus 1 is approximately where ta is equal to theta is equal to 3, based on approximates. And if this is true, then I could say that that's ta s plus 1 is approximately e to the theta s, which is approximately e to the 3s, but that's in the denominator. So if I move it to the numerator, that's e to the minus 3s. So we could do that. We can make those kinds of approximations. And that helps us to create a first order plus time delay function as an approximation of much higher order transfer functions. So I've erased part of the board. I'm going to write out our generalized function that we created though, where g of s can now be equal to our gain times our delay over ts plus 1. And this means that we can approximate these higher order polynomials now in this format pretty rapidly. We can extract out the gain, the time function, and now our delay time. So let's actually think about an example. Say that we were given the following third order transfer function. Third order, pretty high order, but we can turn this into a first order with time delay. So let's say that we are given g of s equal to 6 times minus 0.1 s plus 1 all over 5s plus 1 and 3s plus 1 and 0.5 s plus 1. So we need to identify what the dominant time constant is. This is going to be the slowest time constant, the thing that really holds us back. So think about these and our time constants available. We have T1 is 5, T2 is 3, T3 is 0.5, all based on our denominator because these are in fact our poles. So we need to look for the largest number. And because we see that T1 is greater than T2, which is greater than T3, we're going for the largest, T1. So this has to remain constant. It's stationary, set. Now the other two, we are going to move to the numerator. Additionally, this term, we're also going to put into our e to the minus s term. And that'll be a combination of all three together. So let's go one by one. Minus 0.1 s plus 1 is e to the minus 0.1 times, in this case, s. We just took the term that exists here and we moved it up here. We're going to do the same thing. So the denominator, 3s plus 1, when we move this into the numerator, we'll have to do a change. But for right now, as a denominator term, this is going to be e to the 3s. But to the numerator, that's e to the minus 3s to switch it up, or 1 over that. And 0.5 s plus 1 is e to the 0.5 s, which to the numerator becomes e to the minus 0.5 s. So we have all three of these terms now in the numerator as e's. We need to add them together because they're all going to be multiplied and thus can be added based on our exponential factors. So e to the minus 0.1 s, e to the minus 3s, e to the minus 0.5 s equals, sum those three up, e to the minus 3.6 s. And that's in our numerator. That is this term now. We've accomplished that. Our k was set already at 6, and our ts plus 1 is now 5s plus 1. Thus, our solution is we can rewrite this third order function now in the first order with time delay as 6 e to the minus 3.6s over 5s plus 1. Now, this is much faster to write out. It is much faster to approximate, and we're able to demonstrate a more simplified version of time delay based on our minus 3.6 space unit. This is a lot easier to model. It's always going to be faster to model this computationally, and we can use things like Simulink in MATLAB and other expressional terms to help us to derive this expression. But this is still our transfer function. I mean, this is still now the total combination of the sum of all of these together is now this. This just helps us to decrease the burden as we go from x of s to y of s because this is g of s. And now we can kind of assume maybe what some of the previous pieces could have been. Like we could have probably pulled out pieces of this and figured out this is probably based on three different transfer functions that we put together, either from, a series, or maybe they're in parallel or some combination. But what we've done is approximated down based on what we had already solved, and then we found an even simpler solution where these are going to be approximately equal. I mean, approximations are never going to be perfect, but they're going to be pretty darn good. So that's our expression today on time delays. I hope that this has been really fun, and I look forward to seeing you next time.